Bienvenidos! In the next couple of lessons, we are going to do a quick review of several different types of functions that you have hopefully already seen in previous math classes. The reason we want to look at different types of functions is to just review the sorts of things that hopefully you've seen before so that you can see them again and jog your memory. As we move forward in calculus, we're going to be dealing with a lot of different types of functions, so we want to take at least a little bit of time to review the different types, just to make sure we're all on the same page. And the reason we want to be able to work with a lot of different types of functions is because there are so many different real-world situations that are modeled off of functions, and we want to know which sorts of mathematical models, which sorts of functions might be appropriate in different situations. So let's start with a very simple type of function. We'll look at a linear function. We call these functions linear because when we graph them, the graph takes the shape of a line. And there are different ways to write linear functions, but kind of the standard way is slope-intercept form, which is going to be f of x equals m times x plus b. And when we have a function in this form, for example, f of x equals 1/2 x minus 3, totally fine for this term to be negative. When we write a function out like this, the number that x is being multiplied by, the coefficient, tells us the slope of the line. So in this case, the slope is going to be 1/2. And then the constant term gives us the y-intercept. And once we have those pieces of information, we can sketch the graph. Since we know the y-intercept occurs at -3, we can plot the point 0, -3. That's -3 on the y-axis. And then from there, since the slope is positive 1/2, if we start at this point, we can go up 1 and to the right 2, and that gives us another point on our line. And we can keep using the slope up 1 and over 2 to get more and more points. Let's do that one more time. Up 1 and over 2. That gives us another point. And I'm just going to draw more of them. We can also go in the other direction. We can go down 1 and to the left 2. And this gives us more and more points. And then we can connect those dots in a straight line. And honestly, that is not bad of a drawing for me. Sometimes on the iPad it's a little bit difficult because it's slippery, but I am actually a little proud of that one. So this is the graph of the function f of x equals 1/2 x minus 3. You can see that it is a straight line, and this is true for all linear functions. If we want to, we can talk about the domain and the range of this function. Remember, the domain is all of the x values that we can input, and really you can plug in any number here. You can take any number and multiply it by 1/2 and subtract 3. So our domain is going to be all real numbers. All real numbers. Or if we wanted interval notation, that's from -infinity to infinity. And the range is also going to be all real numbers. If you look at this graph, it is going to keep rising up forever. So we're eventually going to hit any y value you want, or if we wanted a negative y value, we're going to continue going downward over there. So we really do get the whole range of the y-axis. So we can say the range is also all real numbers. And that's going to be true for all linear functions unless the slope is 0. If the slope is 0, we have a horizontal line, and the range is just that number. But that's a special case. If there's no x term here, then really that is just a constant function. And so if it's a constant function, the range is just that constant. But otherwise, if it's a linear function, the range is going to be all real numbers. Now, an example where we're going to be looking at linear functions later on in the semester is we're going to have the graphs of different functions, and we might want to know, I'm just going to draw on the same xy plane. Pretend we've got a function like this. This is some other function. We might want to know if we've got a function and there's a certain point on that function, we might want to know what is the equation of the tangent line to the curve at that point. The tangent line is the line that curve touches only at one point. This is useful for a lot of different reasons. I won't get into those now, we'll see those later, but we might want to know how to figure out the equation for a tangent line, and that's going to involve some calculus, but in the end, what we're going to have is we're going to have a point, and we're going to know the slope, and from that information, we're going to want to find an equation of the tangent line. And to do that, we use the very aptly named point-slope form, which says that if we have a line that contains the point x sub 1, y sub 1, and has slope m, its equation can be written as y minus y1 equals m times the quantity x minus x1. This is a formula that we're going to be using later on in the semester, and so I want to get a little bit of practice doing this right now. So let me show you an example. Let's find an equation of the line that contains the point 6, 10 and has slope -1/2. So we can use point-slope form because we've got a point and we've got the slope. And so here our x1 is 6 and our y1 is 10 and our m is -1/2. So when we plug this into y minus y sub 1 equals m times x minus x sub 1, this is going to be y minus 10, because y sub 1 was 10, the y coordinate was 10, equals the slope -1/2 times x minus x sub 1, which in this case is 6. So that is an equation, but often we want to rewrite this in slope-intercept form because slope-intercept form is kind of the gold standard. So if we want, we can distribute that -1/2 to each of the terms on the right-hand side. This gives us y minus 10 equals -1/2x plus 3, because a negative times a negative is a positive, and 1/2 of 6 is 3. And then to get y alone, we add 10 to both sides of that equation, and this leaves us with y equals -1/2x plus 13. So that is the equation of the line that contains this point and has this slope. When we learn about derivatives in calculus, that will be a tool that helps us figure out the slope of the tangent line to a curve at a point, and that's going to help us figure that out in the end. But we want to make sure we know how to use point-slope form first, so that when we get to those tangent lines, we're able to go through and plug everything in.